Hello students, this is Usha from G.K.Jain High Secondary School, Raipur. Today we are going to learn about the chapter Optics Part 7 in 12th Standard Physics. In this we are going to learn about the interference. Already we have learned what is interference in our last session. Now the continuation of it and double slit experiment and how to find out the constructive interference and destructive interference. Where the bright fringes will be formed and where the dark fringes will be formed will be discussed. 12th Standard Physics Optics Part 7. Two light sources are said to be coherent if they produce waves which have same phase, same frequency, same waveform and preferably same amplitude. Two independent monochromatic sources can never be coherent because they may emit waves of same frequency and same amplitude but not with same phase. This is because atoms while emitting light produce change in phase due to thermal vibration. So they are said to be incoherent sources. To obtain coherent light waves, we have three techniques. They are, first one is intensity or amplitude division. Second one, wavefront division. Third one, source and images. First we'll see intensity of amplitude division. If we allow light to pass through a partially silvered mirror, both reflection and refraction takes place simultaneously. We can use this diagram to explain this. As the two light beams are obtained from the same light source, the two divided light beam will be coherent beam. They are either in phase or at constant phase difference. Instruments like Michelson interferometer work on the principle. So intensity or amplitude we can do by this method. Next is wavefront division. This is the most commonly used method for producing two coherent sources. A point source produces spherical wavefront, which we have already learned. All the points on the wavefront are at the same phase. If 2 points are chosen on the wavefront by using a double slit, the 2 points will act as a coherent sources. It is shown in the diagram. This is the one which we are using for the double slit experiment and all. Next we have see the source and images. In this method, a source and its image will act as a set of coherent sources because the source and its image will have waves in phase. So, the instrument Fresnel biprism used two virtual sources as two coherent sources and the instrument. Next is double slit as coherent sources. Double slit use the principle of wavefront division. Double slit use the principle of wavefront division. Two slits will consider S1 and S2 illuminated by a single monochromatic source S act as a set of coherent sources. The wave from these two coherent sources travel with the same medium and superimpose. The constructive and destructive interference are seen in the diagram. The crest of the waves are shown by thick continuous line and trough are shown by the dotted lines. At points where the crest of one wave meet the crest of other wave or the trough of one wave meet the trough of the other wave, the waves are in phase with each other. So in that place the displacement is maximum and these points appears bright. This type of interference is said to be constructive interference. At points where the crest of one wave meet the trough of the other wave and vice versa, the waves are out of phase. Hence the displacement is minimum and these points appears dark and they are known as destructive interference. On the screen, the intensity of light will be alternatively we have the maximum and minimum. That is, in just like an interference fringes, we have a dark and the band fringes. Next, we'll go into Young's double slit experiment. Young's, a British physicist, used an opaque screen with two small openings called double slit S1 and S2, kept equidistant from a source S. The width of each slit is about 0.03 mm and they are separated by a distance of about 0.3 mm. As S1 and S2 are equidistant from S, the light wave from S reaches S1 and S2 in phase, so S1 and S2 act as a coherent sources, which are the requirement of obtaining interference pattern. So this is the experimental setup. The wavefront from S1 and S2 spread out and overlapping takes place at the right side of the double slit. When a screen is placed at a distance of about 1 meter from the slit, we are able to get alternate bright and dark fringes which are equally spaced appear on the screen. They are called interferent fringes, or they are called as bands. Using an eyepiece, the fringes can be seen directly. At the point O on the screen, waves from S1 and S2 travel equal distances and arrive in phase. These two waves constructively interference and bright fringes is obtained at O. This is called central bright fringe. The fringes disappear and there is uniform illumination on the screen where one of the slit is covered. This shows clearly that the bands are due to interference. Next we will go in for the equation for path difference. So the experimental setup is shown here. You can see the diagram. So S1 and S2 are the slits where they are separated by a distance small d, right? With a light of source lambda, a screen is placed parallel to the double slit at a distance d from it. The midpoint of S1 and S2 is at C, and the midpoint of the screen O is equidistant from S1 and S2. Let P be a point at a distance y from O. The wave from S1 and S2 meet at P either in phase or out of phase depending upon the path difference between the two sources. Now we have to find out what is the path difference. The path difference delta between the light waves from S1 and S2 to the point P is delta is equal to S2P minus S1P. A perpendicular is dropped from the point S1 to the line S2P at M to find the path difference more precisely. Then delta will be equal to S2P minus MP, so which will be equal to S2M. The angular position of the point of P from C is theta, so angle OCP is equal to theta. So in triangle, right angle triangle S1 S2M, the path difference S2M is equal to d sin theta, that is delta is equal to d sin theta. If the angle is going to be very small, then sin theta can be taken as tan theta, which is equal to theta. So from the right angle triangle OCP, tan theta is equal to y by d. Then the path difference delta is equal to dy by d. Based on the condition on the path difference, the point P may have a bright or dark fringes. Now we are going to find out the condition for bright fringes. The condition for the bright fringes or maxima where they have the values or the constructive interferences at the point P to have is path difference delta is equal to n lambda, where n is equal to 0, 1, 2, etc. So we can equate the path difference delta as we have already derived, dy divided by d. So now here it is given delta equal to n lambda. We equate those two, so we'll get dy divided by d is equal to n lambda. Therefore, y is equal to n lambda d by d, or yn is equal to n into lambda d by d. This is the condition for the point P to be bright fringe. The distance is the distance or the nth bright fringe from the point O. Next we will go for the condition for the dark fringes. The condition for the destructive interference or the point P to be have a dark fringes, path difference delta is equal to 2n minus 1 into lambda by 2. Now we will equate with the first equation. So we will get dy divided by d is equal to 2n minus 1 into lambda by 2. Then y is equal to 2n minus 1 divided by 2 into lambda d by d, or yn is equal to 2n minus 1 divided by 2 into lambda d by d. This is the condition for the point P to be a dark fringe. So the distance yn is the distance of the nth dark fringe from the point P. Next is equation for bandwidth. The bandwidth is defined as the distance between any two consecutive bright or dark fringes. Let us find out the distance between n plus 1 and the nth consecutive bright fringes from O is given by. So beta is equal to yn plus 1 minus of yn. Substituting the values, we will get beta is equal to lambda d by d. Similarly, the distance between n plus 1 and the nth consecutive fringes from O is given by. That is for constructive interference. So we will get beta y n plus 1 minus yn is equal to, right? So we will get it as Similarly, the distance between n plus 1 and nth destructive dark fringes from O is given by beta is equal to yn plus 1 minus yn is equal to, substituting the value will get beta is equal to lambda d by d. This equation shows that the bright or the dark fringes are the same width equally spaced on either side of the central bright fringes. So the condition for obtaining clear and broad interference bands are: first one, the screen should be as far away from the source as possible. Second one, the wavelength of light used must be larger. The third one, the two coherent sources must be as close as possible. These are the three conditions for obtaining clear and broad interference fringes. Interference with polychromatic light. So instead of using monochromatic, polychromatic means it gives more number of colors, that is white light. When a monochromatic light is used in interference experiment, colored fringes of various thickness will be formed on the screen. This is because different colors have different wavelength. So however, the central fringe or the zeroth fringe will always be bright and white in color, because for all the colors falling on the point O will have no path difference. Hence, only constructive interference is possible at O for all the colors. Next we go to the next derivation, interference of thin film. Let us consider a thin film of transparent material of refractive index mu and thickness d. A parallel beam of light is incident on the film at an angle I. The wave is divided into two parts. At an upper surface, one is reflected and other one is refracted. The refracted part which enter into the film again get divided at the lower surface into two parts. One is the transmitted out of the film and the other is reflected back into the film. Reflected as well as refracted wave are sent by the film as multiple reflection takes place inside the film. The interference is produced by both reflected and transmitted light. For transmitted light, the light transmitted may interfere to produce a resultant intensity. Let us consider the path difference between the two light waves transmitted from B and D. The two waves move together and remain in phase up to B, where splitting occurs. The extra path traveled by the wave transmitted from D is the path inside the film BC plus BD, so which is equal to 2D. So at this extra path is travel in a medium of refractive index mu. The optical path difference is delta is equal to 2 mu d. The condition for constructive interference is transmitted ray is 2 mu d equal to n lambda. Similarly, the construction for destructive interference in transmitted ray is 2 mu d is equal to 2n minus 1 into lambda by 2. In the second part, for reflected light, it is experimentally and theoretically proved that a wave while traveling in a rarer medium and getting reflected by a denser medium undergoes a phase change of pi, or an additional path difference of lambda by 2 should be considered. So, the condition for constructive interference for reflected ray is 2 mu d plus lambda by 2 is equal to n lambda, or we'll get a value 2 mu d is equal to 2n minus 1 into lambda by 2. The additional path difference lambda by 2 is due to the phase change of pi in rarer to denser reflection takes place at A. The condition for destructive interference for reflected ray is 2 mu d plus lambda by 2 is equal to 2n plus 1 into lambda by 2. So you'll get the answer as 2 mu d is equal to n lambda. Hi students, you all have learned about how to do the expression for the bandwidth. Thank you students. Once again, we'll meet you in the next video.